So I will here show how this so-called AASI program functions. I show you some slides about the operation principle. Then we can do some simulations. But we have to define source types, define what is the material between the source and the detector. I neglect coincidences in this case and how to calculate geometrical detection efficiency. So this is for alpha spectrometry. And especially intended to those cases in which alpha measurements are easy. Easy in the same way as you are doing gamma ray spectrometry. Just put the sample, for example, in the vacuum chamber, measure it and analyze it. No chemical, radiochemical processing. All right. So, advanced alpha spectrometric simulation. I thought that sometimes Finnish persons have a strange level of humor. So what does this AASI mean in Finnish? It means donkey. We are crazy sometimes. Okay, so this code is intended to investigate source properties that influence the shape of the alpha peaks. And sometimes this is very useful when you want to understand, for example, those hot particles that I showed you. You can characterize source properties just doing a spectrum measurement and then try to do some simulations. So you can calculate easily geometrical detection efficiency in different measurement geometries. You can easily generate synthetic alpha spectra, and this is the main thing. When you are doing the simulations, which are very easy to do, it's a good way to train or to understand what's happening in alpha spectrometry. And once more, the code takes into account the properties of the detector and various characteristics of the source and the material between the source and the detector. So this is the operation scheme or principle. The source is here, the detector is here, and medium material is here, if any medium. This is not necessarily present in the simulation. So, in the beginning, let's emit one alpha from the source and draw lots of the location of the alpha particle emission. For example, in this case, in this place. Then the software calculates energy loss in the source, if the source is thick. If the source is thin, there is no energy loss. Very easy, basically. Then if there is some material, then we calculate alpha particle energy loss in the medium. Of course, we have to know the stopping power. We have to know what is the material. Then we take into account detector response and go back. We can do this 1,000,000 times very quickly. And that's it. It sounds very easy. And it is. Oh. So this is coded by using Fortran 90. We have nowadays user-friendly user interface by using Java. And this code has tested in various cases, and we have done many publications which shows that this code is valid. The results are okay. But of course, you have to give correct input information to the code. Most of the data needed for this code, for example, the nuclide library, it's ASCII format, so you can easily change, for example, the nuclide data. Only the main alpha-emitting nuclides are here. I don't remember the number anymore, perhaps 30, 40, 50 nuclides. Okay, how to start simulations? You can start, for example, clicking one of those examples and then just simulate the result, like this. For example, this Thule particle that I showed you, the particle picture is in fact here. Let's open it. Sorry, where is my map? What happened? I cannot see it here somehow. Okay, I can see it there.
You are in PowerPoint now. You should go back to.
Oh, sorry.
Yeah.
Yeah. Sorry. Okay, let's open this spectrum that I showed you already. So let's assume that the particle I am analyzing is spherical particle. I know that the particle shape is more like a potato. But let's assume it's a spherical particle and having plutonium-239, americium-241. And this is the number of decays coming out from the particle. So particle diameter 1 micrometer and density close to 9. So what happens? Let's do this is the measured spectrum. Let's do the simulation. What about the size? Is it correct? Is it 1 micrometer in diameter? No. No. Okay. Let's change the diameter. Could it be something else? Any suggestions? 5, okay.
Point 1.
Point
1 micrometer.
0.1. Okay, let's do it 0.1. Oh, 0.1. Now you can see that the peak shape are very narrow. So definitely this particle is not very small. I will delete these so that we will be mixed, not mixed. Okay, let's assume that the diameter is
0.5.
how much?
0.5.
0.5. As I told you, it's sorry, 0.5 is
So how do,
it's this.
how do we know what exactly is our particle size?
We don't know, but we only have a spectrum, and we assume that it's a nuclear fuel particle or nuclear bomb particle. We don't know basically, in this exercise, we don't know the particle size. How to get it out?
Scanning electron microscope.
Of course. But if you don't have scanning electron microscope, which is quite expensive, then you can do it this way. But let's try to do such as, or to estimate the activity. What should I put here?
5.
5.
Still 10.
This is 4. 10, okay? No, sorry. Quite close.
15.
15, all right. Oh, here. Oh, now we have troubles. What's the correct diameter? But please remember that I showed you in one of the slides that, okay, now I know that this is a potato-like particle. But if you don't know that, you can try to estimate so that particle might be ellipsoidal. For example, this case, you can see the X diameter is 27, Y diameter is 16, Z diameter 9. Okay, it's of course in real life. If you don't know the size or shape of the particle, this is a difficult task. But now you can understand what kind of things you can do with this software.
So can I input a file into this?
Yes.
For example, if I have a spectrum,
Yeah.
can I put it?
Yes, you can. If you are measuring this gray spectrum in your systems, you can put it as an input if in this code.
So what should be the format of the file?
Well, you should check it here. There's an input. I think it's this one result. Oh, this so-called PhD file. These are ASCII files, basically.
You have to convert. You have to convert. Or you can put it to ASCII.
All right, let's go back. I will delete this.
So how do I input and ask the software to pick up a file from somewhere? So
By using this way. You can open.
So suppose we are inserting some file, and from that peak, can we calculate the particle size?
That is what you was doing.
Yeah.
It's the same thing, yeah.
Yeah.
So using that file, we are adding random numbers,
Yeah.
particle
Which is
size,
okay, which is
matches.
fitting.
Yeah, yeah.
That is the.
Okay, I will remove these things and let's go in the very beginning. Let's assume that I have only this polonium source. Let's select the nuclide
So you know the
P polonium here. Let's select nuclide polonium. Let's assume that it emits. Why this is so?
So is that the decay per second? Or
This is total number of decays. In this case, it's 1 million.
per
so-
second or total for
Total
counting time.
number of counts.
Counting time. For counting time.
So it depends on the counting time, of course, but this is total number of emissions that this software uses. And now let's assume a homogeneous source with diameter of
10.
10, thickness quite close to 0, and density, it's not relevant here, but let's assume that the density is 1.
Then it's water.
All right, let's see what is the result. You made polonium measurement yesterday. I haven't seen the result, but let's see what's this. Okay, the result. Basically the same is this.
It is similar.
If the number of decays is much smaller, for example, 10,000 alpha emissions, then the spectrum looks like this. However, if the radiochemical processing was bad, so it was not successful, what might happen? It might happen that the source thickness is larger. Now it's practically 0, but in fact it's of course not 0. Let's assume it's well, not 5.
5 is too much.
All right, let's see what happens. I put 2 extra zeros here. Just do the simulation.
Yes.
The result is this red one. I will remove this blue one. Let's assume that the thickness is 15 micrometers. Do you want to have any other thickness?
100.
100. Okay, let's put it there. Now,
The thickness.
yeah.
Let us see.
Okay, it's very slow in this case because it has to take into account stopping power in this very thick source.
Okay.
And this calculation is not very fast. Okay, I can stop it in this calculator and use a smaller number of alpha emissions. But let's see what happens.
We have
So
time.
what is the side thickness here?
It should appear soon. Let's see. 75, 76. Oh,
So can you remove the other three peaks once?
remove.
Yeah, remove the other red and green and black peaks.
Yeah.
No, not that.
Black,
Yes.
red, and green. So, what's the idea of this? Now, if you done something incorrect procedures in your chemical tricks, sorry, I don't understand chemistry, but you can check that, okay, you can find the reason why you missed. This is just an example. But as you can see, it's a very easy way to do things. Of course, what you can do is that let's check a filter, for example.
Roy, can you put some observing layers and show?
Yeah, okay, let's do that. So, sorry, I have to change this because calculation may take too much time. Let's assume that the sample thickness is very thin, so 0.1 micrometers, and let's put absorbing layers. Okay. Oh, now I have to divide the layer. Let's assume that the density is, I think this is the density of air. Is it so?
Yes.
I think so. But sorry, I have to check one thing. The distance was 3 millimeters. Okay. I assume that the thickness is 5 point. Sorry, it's in micrometers. Now it's close to 6. How many? Is it? Yes, because the source to detector distance was assumed here 6 millimeters. I just put 5.9. And let's assume that it's.
So you have to remove 1 9 from that.
Is it so?
Yeah.
How many nines are there?
There are too many lines.
Uh,
So now it's fine.
no, it's okay.
1 minute. Correct?
And
One more.
layer.
Correct. 6 mm. Correct.
Sorry, I have to check how this is. Let's assume it's composed of hydrogen. I don't want to change it now. Let's do the simulation. So, okay. Let's do first the simulation without this layer. Run simulation. Oh, I will delete the. And now I take absorbing layer into account. What happens? Let's see. I don't know. So, what's this effect? So this is definitely polonium attenuation. All right, I will stop it now and show you some slides. All right, so using this AASI software, you can usually proceed in this way. At first, you have to determine the detector response, then define the source characteristics, then put some absorbing layers, if any. Neglect these coincidences, it's a difficult thing, and then just do the simulation. Very easy. So you can define detector properties. I mean, full width, half maximum. In this case, it was 14 kiloelectron volts, and then tails in terms of also kiloelectron volts. There is in this picture there is only fast and slow component. So this is fast and this is low component. Here are only two tails. So you can select source type, homogeneous source here, radioactive particles, or particles in a homogeneous source like a filter. Select a radionuclide, select a number of emissions. Number of emissions. How to start the simulation? Just run. And you can calculate the geometric efficiency very easily in the same way. Just put the geometry date. So you can delete simulated spectra. You can change the axis values here. This is if you want to put this code in your computer, you can try to do these exercises, which are very easy. We don't go through these here. Three types of source types: homogeneous source, particles in a filter. We studied the effect of particle size. So this is an example how particles may penetrate in the filter. So in a homogeneous case, radionuclides are these, and they are more or less homogeneously distributed. In case of filters, most nuclides are quite close to the filter surface. Material composition. I cannot show it just now, but it can be done easily. Effect of particles in a filter. Material between the source and the detector. No absorbing layers or use it. Simple selection. Please do this later if you want. Just add some layer, define the elemental composition and density and thickness of the material. I neglect these coincidences. And there are some additional features. Okay, run geometric efficiencies at small source to detector distance or large distance. Calculation is very easy. So you can save the generated input file. You can open the desired input file if you are saved it. You can look at other relevant information. Okay, I neglect this one. There is online help, of course. So you can select axis types, colors, etc. So you can also copy the selected file into the Excel or into MATLAB if you want. You can change colors, line thickness in this case. So this is only a small introduction, but AASI can be easily used in a variety of different applications, such as emergency preparedness to generate alpha spectra that may be identical to those obtained in a real measurement case, and training in order to understand the phenomena that has an influence on the alpha spectrum in question, and also in research and technical development. All right, this is it.